So when I define this equivalent class, basically meaning that I will identify the state with another state, but if they are up to the face. So that means that a rigorous state, this size is not a vector, right? The collection of a state is not a vector. Because in the vector, they are not identified with each other. So this make there are some topology about this state. Okay. So this is why in like single qubit case that you will hear people talk about so-called block sphere. So I can like quickly explain this block sphere, but actually it's not so important. Yeah, if you go to some like scientific like video, people will say if I want to describe one single qubit, then I will use a block sphere. And let me explain why. So when you so in a single qubit, basically we are doing like two-dimensional complex space, right? So any state psi can be written as alpha 0 plus beta 1. And if you think this is weird, it's basically alpha beta. And right, so this is and alpha squared plus beta absolute value squared is 1. And if you try to draw all the states, definitely not a sphere, right? You cannot draw this state as a sphere. The reason is that this alpha is complex number. So there are 2 degrees of freedom. There are 2 degrees of freedom. But you only have one condition, right? So you got 2 plus 2 minus 1. So if you try to draw it, it should be like 3-dimensional objects, 3-dimensional manifold, and it cannot be plotted as a sphere. So why people if you go to many video talk about this block sphere? The reason is that this states I write as alpha 0 plus beta 1, but it should be identified with any complex phases times before psi. So that means that it should be I should identify this for any theta 0 2. So that means that I can use this phase. I can try to like gauge fixing or fix this coordination of this. I can use this extra phase to remove the degree of freedom. So since I have this phase, right? So I can use this phase to make this the first coefficient between this cat 0 to be real. Right? Because if alpha is complex, then I can just find the theta such that this theta will absorb the complex part of this alpha. And then not only that, I can make this alpha to be positive, to be greater or equal to 0. Because if alpha is minus 1, then I just choose theta to be pi. Right? So that means that I can always make alpha to be greater or equal to 0 by choosing the appropriate phase. So I can make this side to be cosine theta divided by 2, right? Because it's -1, but so I can just choose a phase. Let's say theta is 0 to pi here, right? Because I can always choose it to be positive. Now, if I choose this to be here, then this beta need to be square, right? It need to sum to be 1. So the absolute value for this beta must be sine theta divided by 2. But there should be an extra phase relative to beta and alpha, right? They say I choose alpha to be real, but beta can still be arbitrary complex, can still have a phase. So you can place that here. And if you plot it, then you get theta and the phi. And these theta and phi are basically you can express as a spheral coordinates. Okay. So now you can like place the states. You can place any pure states called alpha 0 plus beta 1, but identify with phase, then you can plot this single qubit state on a sphere. So for example, this guy is 0, and this guy is 1. Okay. So this is why people like using this block sphere. It looks good, right? Because now you can view like 4-dimension, like single qubit on the sphere. But this is not useful because if you're doing like if you have like multiple qubits, then it will be very difficult to plot it. And the multiple qubit is not their topology is not a sphere. It's not easy to describe the multi-qubits topology. So this kind of like block sphere is like somehow like good for illustration, but not so useful. Okay, so this is a state, right? So this axiom just say that any states. When I say a pure state, I would just say that it's finite dimensional. And so at least in this course, we are only talking about discrete variable. Up to like maybe final few lecture. But now I'm talking about a finite dimensional object, so state just this. And the second axiom is evolution. So let me just go into evolution. This is simple. I think everyone knows. So and in quantum mechanics, right, we are the evolution will be described by a thing called so-called Hamiltonian. So let me just write something. So this should be this is so-called, it's basically a postulate. Oh, postulate. So this postulate says that the state evolution is described by a unitary u echelon psi. Start. And this is the same and okay, so this basically is everything. So this evolution axiom just say that whenever I give you a state psi, the only allowable process is that I take some unitary and apply on psi. And why unitary? Because this psi should be viewed as a n-dimensional complex number, but up to the identification. So this u psi should preserve the length, right? So everyone knows about unitary will preserve the length of the complex vector, because the definition of unitary is that u dagger times u is identity. So if you do this, so now I will keep using bracket notation, right? So this side. So the length is the same. Okay. And this is the same as your usual quantum mechanics, right? Because your usual quantum mechanics will just say that there is a guy called Hamiltonian, and which is Hermitian, and there's a Schrodinger equation, right? So it's basically this. And I will choose h bar to be 1, just for the convenience, right? So this is a Schrodinger equation, and if you write it, say you have some t, you can write as exponential, whatever, right? If it's time independent, then I can write as this, as a t0. And this guy is basically unitary. This guy is unitary. And the reason is that this h is Hermitian. So if you do this, this is u, right? So if we do u dagger, then basically it's just h t, but h is Hermitian. So u dagger is exponential iht, and the u dagger u will just be exponential iht as exponential negative iht, which is exponential to the power 0, which is 1. Okay, so notice that in finite dimensional case, this h will just be some n by n matrices. Let's say your complex n dimension, right? So h will be n by n matrices. So usually two matrix exponential are not commute. You cannot commute both. But in this case, since they are the same, so we can just do the commutation. Everyone's good for this, right? So this is why Hamiltonian need to be Hermitian. So if I take a Hamiltonian, then I use the Schrodinger equation, and definitely the state evolution can be written as some unitary applied on original state. And good. And conversely, is any finite dimensional unitary matrix, there exists the n by n matrix which is also Hermitian, such that u can be written as exponential minus times ih, or my times minus. Is it? So this is also obvious. The reason is that this unitary is normal, is a normal matrix, right? If this unitary is a normal matrix, so you can diagonalize this u to be some matrix SAS with the eigen and S dagger, and these are the eigen states. Sorry, the eigenvalue. Lambda 1, lambda 2, lambda 8. And since U is unitary, so all of these lambda I have the modulus 1. So I can write all these lambda I to be used to be some exponential minus I theta I. Okay, so that means that I can write U as exponential minus I theta 1 dot, 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 with exponential minus I theta n, and S dagger is all 0. So that means that I can write U as S times exponential minus something just theta 1 dot, 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 theta n, and S dagger, and then these are all 0. Now I can combine everything to exponential minus I S theta 1 dot, 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 theta n 0 0 S dagger. Then I can say this guy is H. So any unitary, then I can just this is trivial, right? So everyone knows about it. So all of this is everyone knows about it. Right, so the definition of matrix is exponential. When I write A here, then you use the Taylor expansion to give the definition. So for any n by the matrices, it's a complex number. Yeah, I can just define this as a matrix exponential, right? Everyone knows about this. And yeah, and okay. So and if you take any like unitary or the inverse, right, it's easy to see that it's easy to probably it's not so easy. So take S, right? So it's the obvious relation. If you take power k, SA as inverse power k, well, you just be SAK as inverse. This is trivial because when you write the k equals to 2, then you get SA as inverse and SA as inverse, and then this S and S inverse will cancel with each other. So that means that if S is unitary, then if you apply on it both sides, then you can just maybe found this. Right, because this guy is true is right, because I sandwich with S and S inverse as, and this will be S inverse K, and using this relation it's the same, so it will be just definition. Oh, so I just call this to be Hamilton. Using this notation, I just call this to be Hamiltonian. So this means that it's the same as, so infinite dimensional, that every unitary is just, if you use this kind of relation, then this is compatible with this Schrodinger approach. So this is why in quantum information that people seldom talk about Hamiltonian, right? Because Hamiltonian is somehow like equivalent, using this relation looks almost the same as the unitary. Okay, so up to now that we already finished the first two, right? The first two like axiom. So the final ingredient is the, oh, let me just try to add more. Is it? Let me see. Sorry about this. Okay, so the final ingredient is the measurement, right? It's the measurement. Since we already talked about everything, right? So the rest is the final mysterious part is the measurement. And there are three like different way to talk, three different levels of the measurement. So I was use the okay. So there are like three different level, and there are basically each one is generalization of previous one. So let me just level one, right? So so what level one is that as we know that each state looks like this, right? As a vector, a normalized vector, and up to the face defined to be a complex number. The level one is that I say that I have I pick, let's say I pick V1, V2, let's say Vn as a also normal basis. So also normal basis of this C to N. Then I say that the probability that I get outcome D is basically the BD inner product with psi and the square. Definition. So this is somehow like different from it's the same as your quantum mechanics, but use mathematical axiom to pack them. So this level one just say that if level one say that wherever you choose like n dimension, if you try to use this n also normal basis to measure the states, the probability that you get the outcome D is you just take VD, that vector, do the inner product with the state psi and then take absolute value. So this is the probability. And this is not the end of definition. The crucial part is that after you measure the states, psi will collapse to one of to VD. So what this means is that you just do the measurement, and for each D you get some probability. The probability that you get outcome D is this square, and after this measurement, the state will collapse to VD. This is the most weird part in the quantum mechanics. So the most weird part is let me just say something. So this is well defined. Why? So remember that the states are equivalent to this, right? Up to the phase. But when I say the probability, when I do this guy, right? Since I take absolute value square, so it's the same as you take VD with exponential I theta and take the phase. But this is the same because this term take absolute value square is 1, right? So this is well defined. So it's like in mathematics when you write different axiom, right? You need to make sure that there's no contradiction, right? So for example, if there's no so this means that this square is somehow like the important thing, because otherwise that probably you get some contradiction. And also this is a valid probability distribution. Valid probability distribution. So for a discrete probability, the condition for a discrete probability is that they are all greater or equal to 0, and then they're sum to 1, right? This is called a probability vector. So for example, you throw a dice, then whether you get 1 to 6, each one is the same as each one has the probability 1 divided by 6. So they are all greater or equal to 0 and also sum to 1. So obviously that each of these guy is greater or equal to 0, and it's also sum to 1. D from 1 to n. And why this is sum to 1? So remember that the previous yesterday lecture that I talked about so-called resolution of identity, right? I say that you take any orthonormal basis, you write this notation, this projector will give you 1. So obviously that if you take psi, which is 1, the same as D from 1 to n, you take psi VD psi, right? So it's D from 1 to n. These are complex conjugate, right? So it's well defined. Okay. So this meaning that I'm not saying something stupid. I'm saying that this is So after upon now, right? Up to now, everything looks like good. It's well defined, it's probability distribution, and it's also correctly represent this extra phase. So all the mysterious part is this. The state collapse, right? I say that after you you get some outcome, the state will collapse. And basically, you can go online and find some other paper. Basically, you can also define your quantum mechanics without final sentence. You can say that I get probability outcome D, but the state will remain the same, right? So if I delete this collapse, then there's no other like obstruction or there's no other contradiction. So maybe in the future that I can show some simple example in quantum computing. If you remove this collapse condition, then your quantum computing will be extremely powerful, but it's still not powerful to solve some NP complete problem. So this is why so there are some people that study this kind of quantum computing, so-called non-collapsing measurement. So what I want to tell you is that this collapse is very unnatural. You can still remove this, and you do the same thing. You can say, oh, I get outcome probability, I get outcome D with some probability, but the states will always the same. Then your computation will be like so much powerful compared to basically the limitation of quantum computation is that wherever you do the measurement, the states collapse to. So then you need to redo the computation again, and then you measure and you collapse. So this collapsing actually reduces the power of quantum computation, right? Because wherever you measure. Okay.
It's possible it would not collapse in reality in real life.
I'm not sure. I don't think. But actually, it's like if you have a state psi, and somehow like you know some information of psi, then you can try to choose one of the VD which is very close to psi. Then these states will not perturb a lot by this, right? But this non-collapsing measurement is interesting theory. You can so I will show one example in the future that there's an algorithm called Simon's algorithm. If you have non-collapsing power, then you can solve this Simon's algorithm like just like simple just one query. But the standard quantum computation will take like n queries. Okay, but that previous one is not the quantum mechanics, not the usual measurement, right? So let me just talk about level 2. So this is the usual quantum mechanics. And there's a name called projective measurement, or PVM. It's projective measurement, PVM. Right, so in the quantum mechanics, remember what you learned is that in quantum mechanics, you still have a state psi n, but you are given the operator or Hermitian matrix is M, and then you are given M, which is Hermitian. And what's the results? And then so in the quantum mechanics, right? The professor tell you that you just diagonalize it. The states will, if I use M to measure these states, the states will collapse to one of the eigenvector of M and get the outcome with that eigenvalue, right? This is the same. So let me just write down. The state psi will collapse to eigenvector Vi of M with eigenvalue. So basically, the measurement result is lambda I. You will get lambda I, and after that state will collapse to that eigenvector. This is a standard quantum mechanics, right? So this is why Hermitian is important, because this lambda I is some results that you will measure in the lab. So lambda I must be real, right? Otherwise there is contradiction. And so notice that level 2 is the same as, is actually equivalent to level 1, right? You just pick that, in level 1, you just diagonalize M and take all these eigenvector of M and as a level 1 input. So the level 1 input is I pick the orthonormal vector. Then in level 2 is the same. So there's no contradiction here. The only difference is that I pack In level 1, I give D orthonormal basis. In level 2, I just pack this D orthonormal basis into one matrix M. And I say the outcome is down the I with the product being the same. Oh, by the way, so in this just still be recorded. So I just recall that in quantum mechanics that you can also study this so-called absolute value of M, right? Because you get lambda I with probability. Let me just write down, right? You get lambda I with probability this. Okay, and it's yeah, basically it's easy to prove that it's this. Is this so obvious? So I believe this is obvious expression that you see in quantum mechanics, and this is the definition, right? However, this is the definition. You get outcome down the I with probability this guy square. So this is expectation value. So I would say that oh, maybe let me just quick prove they are the same. Proof. Actually, it's trivial. Let me see. Right. So one way to do this is write down a spectral decomposition. It's trivial. Right. This is a spectral decomposition, meaning that M is Hermitian, right? So if I take all its eigenvector, then I can combine as a projector and times the eigenvalue. So this M will be the spectral decomposition, and you just plug in. So M psi, you just sandwich both sides, right? So this is why bracket notation is powerful, that you get I from 1 to D. Psi bi absolute value squared on the I. So everything is consistent. Okay. So finally, we can have so up to now, the level 1 and level 2 are the same, and they're also the same as your quantum mechanics, right? So there are level 3. So this is somehow like a generalization of the measurement. And I think it's only like shown in the quantum information lecture. And it's a little bit hard to describe. So let me just see how I can, I guess. So this, so level 2 is called a PVM. It's called projective measurement. And why it's called projective, right? Because all these guy, all these VI dot VI, these are projector, right? VI square is the same. So they are projector. And level 3 is called POVM, for the positive operator measurement. So this is called positive, I think it's POVM formula, yeah. Okay, positive operator value measure. So let me just write down positive operator value measure. Okay, so okay, let me see. Okay, so let me just this. So this POVM is much more like generalized. So let me explain. So I still have state psi, right? But now I will give you like EM. These are operator or the matrices. Let's say the number of EM can be very large or very small. It's fine. And so these EM are basically Hermitian. Is it Hermitian? Yeah. Let's see. Yeah, I think it's Hermitian. And it's also positive. So positive meaning that all the eigenvalue are greater or equal to 0. And this satisfies this relation. They are sum to 1. And what I'm saying is that, so let me just write down. So the probability you get outcome. So now I'm using M as label, right? You get outcome M is psi E M psi. Okay. It looks maybe a little bit confusing. So in this POVM, why what I give to you is that I give you a bunch of positive matrices. Positive mean that there are positive semi-definite, right? So there are all eigenvalues are greater than 0. And the requirement are this EM, they are sum to 1. So notice that there are this M not need to be like D that, not need to have like n of them. This EM can be arbitrary, can be like small, only 2 of them or 3 of them or 4 of them. But they are sum to 1. And I say that the probability you get outcome M is basically this guy. And okay, so now we can check whether it's like valid, right? So valid because it's the same whatever side back to this, and this is the same, right? It's still the same. Because you take a broad will give you exponential minus I theta. So it's the same. Okay, so it's well defined. And since EM are positive semi-definite, right? So this guy is also greater or equal to 0 for all M. Since EM is positive semi-definite matrices. And finally, how about the probability need to sum to have 1 equals to 1, right? And by my assumption, that I say all these EM are sum to identity. So it's like a trick, it's like a little bit trick, but basically definition, which is size 1. Okay, so it's still valid, still valid, right? Okay. So it's this is POVM. Okay, so what I'm saying is that this PVM is a subset of POVM. Okay. And the reason is that is it so obvious? Okay. The reason, let me just read it. So the reason is that this level 3 is a generalization of level 2. Because in level 2 that I give you M, right? Then you just say that oh, it's VI is the projector PI. Then so you can just pick, let's say EM to be, let's say, VM and VM. Now, obviously that the sum over this EM, now you have M from 1 to N, right? So if you sum over this EM, then you get the same thing. It's resolution of identity. And this all the EM are also PSD. Because they are projector, right? They square equals to 1. So their eigenvalue can only be 0 or 1. Right? So from this picture that you said, you can see that this PVM is actually the special case of this POVM. By just picking the projector of, I give you PVM, you just take all the projector as this EM. So now you have 1 to N EM. Then there are sum to 1. Right? There's sum to 1. And then there are also PSD because they are projector. Their square is the same. It's the same as self. So P square equals to P. So their eigenvalue is either 0 or 1. Okay, so this is interesting. This is interesting thing. So in sometimes that in quantum, basically in quantum information, that we will use so this is so-called generalized measurement. This is PVM. But there's a problem here, right? I only tell you that the probability that you get the outcome M is this. I didn't tell you that after you get this, after you do the measurement, what will state change? So this definition is unfinished, right? Remember that the previous two, the level 1, they give you the also normal basis, and you will collapse to one of the eigenvalue, one of the eigenvector. And in level 2, I give you 1 Hermitian matrices. And it's trivial that in quantum mechanics that you know that the state will collapse to one of the eigenvector. But in this PVN, I do some trick on mathematics. I just give you a bunch of positive operator matrix, positive value matrices, and there are sum to 1. And I tell you that is a probability. But I didn't tell you that what's the state. What's the state? Okay. So let me just, so I need to, okay, so I need to specify, right? I need to specify what the what's the states after the POV measure. Uh, is it good? Good. Okay. So let me just write down. Up to now it's good. Okay. So the states will be, let's say you get outcome M, right? You get outcome M, then the state will be collapsed to one of, okay, I should say the states will be, yeah, will be the following. What it is. This. Okay. And okay, so this is the axiom. And then let me show you this is equivalent as the PVM, right? So let me just do the check. It should be, hopefully it's not so difficult. Okay, so remember in the PVM that this EI use I will be just, let's say VI, right? And let me see how I can write as this. Right, yeah. So let me just right. So if I use this, right? So remember this is the EM corresponding to the PVM, right? So now what's this EM guy? Will just be VI guy, right? Okay. And this the numerator is square root of 2. Sorry, not square root, square roots this EI, right? So basically it's just VI this square and take a square root, and it's the same as VI. So in this case, that these post measurement states will be just VI this. And numerator is basically the denominator is the same, right? Nice. So we get VI. Right. So this means that this is this is the same as the previous level 2 measurement. They are all consistent. If I take the post measurement state of this EM side divided by the square root of this guy, if you take the project side to be, you use the PVM, then PVM will basically they are compatible. By the way, so this part is somehow like confusing, but so I will upload notes that you can check. So just quick recap. So in PVM, that the one way I can say is that I give you a bunch of projector, right? So in PVM that we have a set of projector. Let's say I use let's say I have pi I projector, and the projector condition is that they are square are the same as itself, and that they are also orthonormal to each other. That there are delta ij, and they are all sum to 1. So this is a PVM. And if you want to go back to the standard bracket notation, that you just imagine that this pi I is the same. It's this kind of thing. And for a POVM, I give you a bunch of EI matrices, then there are sum to 1. By the way, they don't need to have D of them or N of them. They are sum to identity. And the only requirement is that they are positive. So compared to 2, right? The only difference is this PVN is obviously like more generalized because this POVN don't have the orthogonality relation, and then this EI can be very small. You can have 3 of them or only 4 of them. So I don't have time, but let me see. What's the time? Ah, okay, it's almost finished. Okay, so next week, well, I will show a small example of this PVM, some non-trivial example. And after that, we will like go to building inequality. Nice shot. And I will make a report online. If you have any question, then you just come to ask me.